Welcome to this comprehensive lecture on the hydrogen atom spectrum. Today, we are going to explore exactly how a simple atom produces a unique, colorful fingerprint of light. We will build our understanding from the ground up, discovering how this incredible phenomenon bridged the gap between classical physics and the strange new quantum world. By the end of this video, you will understand the math behind the glowing lights of the universe. To understand how atoms emit light, imagine walking down a staircase in the dark while holding a glowing ball. You can only stand on specific steps, never floating in the air between them. If you jump down, the ball flashes a specific color depending on how far you fell. In an atom, the steps are allowed energy levels, and the person jumping is an electron. Because the steps are at fixed distances, the electron releases very specific colors of light, creating a unique fingerprint called a line spectrum. Now that we understand the concept of energy steps, let us look at the mathematics behind them. Niels Bohr proposed a revolutionary model with a specific equation for the electron's energy. In this formula, the energy depends on several fundamental constants: the mass and charge of the electron, vacuum permittivity, and Planck's constant. The variable n is the principal quantum number, which simply represents the orbit number. The negative sign is very important. It shows that the electron is bound to the nucleus. As the orbit number increases, the fraction gets smaller, meaning the energy becomes less negative, and therefore higher as it moves further away. This energy equation leads us to an important realization about the light we can actually see. Depending on which lower orbit the electron falls into, the emitted light is grouped into different spectral series. If the electron falls all the way to the first orbit, it releases a massive amount of energy, producing invisible ultraviolet light known as the Lyman series. If it falls to the second orbit, it produces visible light that our eyes can detect, called the Balmer series. Drops to the third, fourth, and fifth orbits produce infrared light, which we feel as heat. Before we move on, let us see this with a concrete visual. Here we have a diagram summarizing how these spectral series are formed. The horizontal lines represent the allowed energy states, or the steps on our staircase. The vertical arrows represent the electron jumping down to a lower energy state, releasing a photon. Notice that the jumps ending at the first level are the longest. This means they release the most energy, which perfectly corresponds to the high-energy ultraviolet light of the Lyman series. Now that we have visualized the jumps, let us introduce the standard mathematical tool used by chemists to predict emission spectra. This is the famous Rydberg equation. Conceptually, it is derived directly from the energy differences between orbits. It tells us that the reciprocal of the wavelength is equal to the Rydberg constant multiplied by the difference of the inverse squares of the final and initial orbits. The Rydberg constant is a massive fixed number, while the orbit numbers change depending on the jump. By simply plugging in whole numbers for where the electron starts and ends, you can predict the exact color of light the hydrogen atom will emit. Let us apply this formula to a real problem to see how it works. We need to calculate the exact wavelength of the first line in the Balmer series of the hydrogen emission spectrum. We know from our previous definitions that the Balmer series corresponds to electrons falling down to the second energy level, so our final orbit is 2. The phrase first line means the smallest possible jump, which must come from the very next level up, so the initial orbit is 3. We set up our Rydberg equation and substitute these orbit numbers along with the standard Rydberg constant to begin our calculation. Continuing with our calculation, we must carefully perform the basic arithmetic inside the parentheses. Squaring the initial and final states gives us 1/4 minus 1/9. We find a common denominator of 36, which simplifies the geometric part of the transition to exactly 5/36. Multiplying this fraction by the Rydberg constant gives us the wave number, which calculates to 1.523 times 10 to the 6th inverse meters. It is crucial to remember that this is not the wavelength yet. It represents how many waves fit into a single meter. To find the actual physical distance of the wavelength, we must perform one final mathematical operation. We take the reciprocal of the wave number by dividing the number 1 by our previous result. This inversion step is crucial, and it is where many students make mistakes. The calculated wavelength is 6.56 times 10 to the negative 7th meters, which is equivalent to 656 nanometers. In the real world, this perfectly matches the bright, intense red line visible when looking at glowing hydrogen gas through a prism. This is a beautiful example of mathematics predicting reality. Let us look at another example, this time calculating ionization energy. This is the energy required to completely remove an electron from the atom. The electron starts in the ground state, orbit 1, and is pushed to an infinite distance away. Because we are putting energy into the atom, we use a slightly modified Rydberg equation, swapping the initial and final states so our result remains positive. We plug in 1 and infinity for our orbits. In mathematics, dividing any finite number by infinity results in 0. This means the term representing the final state completely vanishes, leaving just 1 minus 0 inside the parenthesis. Physically, this means at an infinite distance, the electron feels 0 pull from the nucleus. The wave number is exactly equal to the Rydberg constant. To convert this wave number into an actual energy value, we rewrite the standard Planck-Einstein energy equation to multiply by the wave number directly. We now substitute all the known fundamental constants into our rearranged energy equation. We multiply Planck's constant and the speed of light by our calculated wave number. This final multiplication yields the exact amount of energy a single photon must possess to knock an electron completely out of a hydrogen atom. The result is 2.18 times 10 to the negative 18th joules. If you scale this up to a full mole of atoms, it perfectly matches the experimentally measured ionization energy of hydrogen gas in the laboratory, proving that our theoretical framework is absolutely correct. Now that we have successfully used the Rydberg equation in multiple examples, let us understand where it comes from by deriving it from Bohr's original model. This chunk of the proof establishes the foundation using the law of conservation of energy. The energy of the emitted photon is exactly equal to the difference between the initial higher energy level and the final lower energy level. We substitute Bohr's full mathematical definition for both states. The two negative signs on the second term cancel out to become a positive. We then factor out all the shared physical constants to isolate the changing orbit numbers, setting up our next step. This next chunk of the proof connects the invisible energy of the atom to the visible light we can actually measure in a laboratory. In spectroscopy, scientists measure wavelength, not energy directly. We bring in the famous Planck-Einstein relationship, which states that energy equals Planck's constant times the speed of light divided by wavelength. By setting this equal to our factored Bohr equation, we bridge the gap between energy and light. We can then solve for the wave number by dividing both sides of the equation by Planck's constant and the speed of light, which groups all of our constants together on one side. We have reached the final step of our derivation, where we define the constants. Look at the massive fraction on the right side of our equation. Because it is made entirely of fundamental values like electron mass, electron charge, and the speed of light that never change, the entire fraction is just one big constant number. We define this massive fraction as the Rydberg constant. Substituting this symbol back into our equation gives us the final result. This proves that Bohr's theory of quantized orbits perfectly derives the experimental Rydberg equation, showing exactly why the formula we used earlier works so well. So we have proven that Bohr's math holds up. This brings us to why this matters in the real world. The hydrogen atom spectrum is the foundation of modern astrophysics. When astronomers look at distant stars, they cannot collect physical samples. Instead, they pass starlight through a prism and look for this specific barcode of lines. If they see the Balmer series, they know hydrogen is present. Furthermore, if those lines are shifted toward the red end of the spectrum, it proves the star is moving away, showing us that the universe is expanding. Let us summarize the key takeaways from this topic. First, electrons in an atom can only exist in strictly quantized energy orbits. Second, when an electron falls to a lower orbit, it emits a photon with a very specific wavelength, creating a distinct line spectrum. Third, by combining Bohr's model with the Planck-Einstein relation, we can mathematically predict these exact colors using the Rydberg equation. You have now seen how abstract quantum math perfectly describes the colorful light we observe in the universe.